All right, it's 2:02 with over 30 attendees. Hi, welcome everyone to ASIC seminar series. I'm John, the seminar coordinator. I will be moderating the seminar with Cassie, who is our communication manager. Just so you know, the seminar is being recorded and we will publish the recording on our YouTube channel. And after the presentation, there will be a Q&A session, so please feel free to ask any questions. And before the speaker gets started, I will make Cassie give you more background about the speaker. So Cassie, please go ahead.
Thanks, John. So I'm excited to introduce our speaker today, who's Dr. Andy Thomas. So Andy is the John S. and Sherry Chen Professor of Environmental Science and Engineering at the California Institute of Technology and the Director of the Lynch Center for Global Environmental Science. His research uses a combination of seagoing observations, satellite remote sensing, and idealized numerical models and theory to study the physical processes by which the ocean couples to and influences other components of the climate system, including the atmosphere, cryosphere, and marine ecosystems. Thompson's research group is particularly interested in high latitude processes, including the impact of ocean turbulence on the evolution of sea ice in the marginal ice zone and the pathways by which the ocean transports heat to the grounding zone of the Antarctic ice sheet. I'm just going to go ahead and turn it over. Thanks, Andy, for being here. Thank you, everybody else. Please enjoy the talk.
All right. Thank you so much, Cassie and John, for doing the introduction. Let me just get this up. And can everyone see that okay?
Yes, we can.
Awesome. All right. Well, thanks so much for the invitation to give this presentation today. I'm really looking forward to sharing some of the work. I've decided to talk today a little bit about some of our group's larger scale oceanography work. And so I'm going to be talking today about the ocean's global overturning circulation, and in particular, its three-dimensional structure, but really focusing on what causes transitions in this overturning and how that impacts sort of the global response in terms of the climate system. So this is work that I've had the pleasure to work on with a number of students, postdocs, and colleagues at Caltech. Some of them are listed here. The work I'm going to show today is largely led by a former postdoc, Shantong Sun, who's now at the Loshan Lab in China, and also Dave Bonin, who graduated with his thesis from Caltech in the spring and will be doing a postdoc at the University of Washington. And then, of course, important insight from a number of the people that are here. So one of the main messages I really want to try to convey in this talk today is the importance of the ocean's stratification in terms of not only the mean structure of the overturning, but also how it responds to perturbations. So in order to do that, I really wanted to start here on this first slide, which is actually just showing a picture of the ocean's stratification. So what you're looking at is a hydrographic section through the Pacific Basin. So imagine taking a knife almost and slicing it down through the Pacific Ocean, opening it up and looking inside. So you have depth on the y-axis and latitude on the x-axis, spanning 60 degrees south up to the north. And what you see is that there are a couple of key features. If you look near the surface, you sort of see this bowl-shaped structure of the stratification. That's mostly due to the ocean gyres. We're going to be talking mostly about processes that are happening below those gyres. But when you look into the ocean interior, there's two very distinct structures you see here. Throughout most of the global ocean, density surfaces are flat. You have a dominantly vertical stratification, and we're going to talk about a little bit about the importance of water moving up across that stratification. And then the one region of the ocean where you get this big difference from these flat isopiktals is in the Southern Ocean, and that's associated with the Antarctic circumpolar current. You see that on the left, where you have these steeply tilted isopiktals, which take, or at least provide a pathway for deep water to come up to the surface. So we're going to kind of have this picture in our head. But now I want to spend a few minutes and just kind of go through a little bit of the history of our understanding of the overturning circulation. So what I'm showing here is sort of a classic figure by Arnold Gordon from a paper in 1986. This was some early work that Arnold was doing with Wally Broker at the time that also led to the very popular conveyor belt schematic that most people will be familiar with. And I just want to point out that even at this early period, it was very strongly appreciated that the overturning was a three-dimensional picture. and that it involved exchange between the different ocean basins. So in particular, there was an asymmetry in the sinking where deep water formation happens in the North Atlantic and where waters sink, and then this much broader distributed upwelling. And one thing that's important to keep in mind is that the Pacific Basin or the Indo-Pacific Basin as a whole is just a much wider surface area just due to the geometry of the continents. And therefore, most of that upwelling that would return waters back to the surface were thought to occur not in the Atlantic, where deep water formation happens, but rather in those other basins. And of course, the Southern Ocean was this important route for exchanging water between the different basins. One thing that these early schematics neglected, though, is sort of thinking about the importance of the Southern Ocean, both for bottom water formation. So you can see here in the schematic that there's no representation of sinking around the margins of Antarctica, which we know today is obviously quite important. But also this idea of upwelling along those tilted density surfaces that I showed in the previous slide was not yet appreciated. So again, this picture came out in sort of late 80s, which is around the same time that we were beginning to get our first direct estimates of how much mixing is available to actually return those waters back across the stratification. And one of the main surprising results from those early studies was that that mixing appeared to be about an order of magnitude too weak for the predictions that had come out sort of in the 1960s. And so this gave rise to what I refer to as the missing mixing error. Like, where is that mixing happening that allows water to rise back up across the stratification? And one response to that was that the mixing in the ocean was much more spatially heterogeneous than we had previously thought. And here's just a very well-cited paper led by Kurt Poulsen that came out in Science in 1997. What you're looking at here is a map from the Brazil Basin. So depth is on the y-axis, and then you're looking at a section that's extending on the left from the coast of Brazil out into the interior of the Atlantic Basin where the mid-Atlantic ridge is. You're looking at colors here as an estimate of the sort of turbulent diffusivity in the ocean interior, but it's a proxy for how much mixing there is. And what you can see is that over most of the ocean, you have these low values, which are less than 1 times 10 to the minus 4, which is sort of the predicted value. But yet when you get over rough topography, there's enhanced mixing. And so there was a lot of work trying to understand if we went to a number of different places in the ocean, could we accumulate enough strong mixing locations to close the overturning circulation? And this remains very much an active area of research. But along this, at the same time, there was sort of a second explanation for why we didn't need as much mixing in the interior to this upwelling. And that was the importance of the Southern Ocean. And in particular, this idea that water masses that were in the deep ocean could come into the Southern Ocean, where you had these very strong tilting density surfaces, and they could move up along those density surfaces to the sea surface without having to move across the stratification. And bringing in the Southern Ocean, again, because the Antarctic circumpolar current is, in fact, a circumpolar feature, it very much motivated what I would refer to as a zonally symmetric or a zonally integrated view of the overturning circulation that gave rise to this sort of schematic picture that I think has been very important over the last 20 years or so, where depth here is on the y-axis, you have latitude now on the x-axis, and you can see schematically, at least, that the overturning circulation is made up of these two different overturning cells, an upper cell, which is clockwise in this picture, and a lower cell, which is counterclockwise. Now, importantly, these two cells are associated with different dynamics, and that upper cell is sourced by making deep water in the North Atlantic. But in the schematic, they sink along density surfaces, which are these white lines, that move through the Atlantic Basin. And when you move into the Southern Ocean, those waters again move along density surfaces, come up to the sea surface. And that overturning circulation can be closed without any movement across density surfaces in the ocean interior. This is what we call an adiabatic cell. In contrast, when we look at the lower overturning circulation, you have dense waters that are feeding the abyssal ocean, but they do so in density classes that do not outcrop anywhere else in the global ocean. So waters that sink into the abyss here, the only way for them to come back to the surface is to actually move across the stratification. And so we refer to this as a diabatic cell. It's associated with this upwelling Antarctic bottom water across the stratification. So even though this picture has been very important for sort of highlighting the role of the Southern Ocean, I think one thing that it has done is it sort of obscured the fact that we really still have this three-dimensional overturning circulation. And so in that previous picture, you had this view of these two cells being stacked vertically, with an upper cell being sourced by North Atlantic deep water, a lower cell being sourced by Antarctic bottom water. Whereas in reality, in the global ocean, these cells are not stacked vertically, but rather they are stacked zonally. So what I'm showing here is the diagnostic of the global overturning circulation from NCAR's CESM large ensemble. And now I'm breaking up the overturning, not taking a full zonal or longitudinal average, but actually breaking it up into different basins. And what you see here is in the Southern Ocean, you do have this picture of a stacked upper cell, which would be clockwise, and a lower cell, which would be counterclockwise. But that upper cell is dominantly occurs in the Atlantic Basin, as indicated by this red clockwise circulation. And in the Indo-Pacific, you have an overturning circulation of the opposite response, is associated with bottom water coming in at these lower density classes, rising up through the stratification and flowing back out to the south. And what I'm going to argue today is that the response of the overturning circulation to a perturbation depends very strongly on this three-dimensional structure. And then the last thing I'll just mention here, this three-dimensional picture has been revisited, and really you can see it as a constraint on, you can think of it as the heat or the buoyancy budget in the ocean. If you look at these curves on the top here, what we're plotting is the distribution of the surface buoyancy flux, so you can think about it as the heat flux, as a function of latitude, again, at the ocean's surface. And again, because of this difference in basin geometry, the Atlantic Basin is much narrower than the Pacific, but it also expands much further to the north. If we integrate over the Atlantic Basin, the surface heat flux is a region of net heat loss. Whereas for the Indo-Pacific, because we have this much wider region in the tropics, we have a region of net gain into the Indo-Pacific. If we expect the ocean to come into some steady state, that implies that there needs to be an export of heat from and buoyancy from the Indo-Pacific and an import of that heat or buoyancy into the Atlantic. So if you look at these lower panels here, the colors are showing the same structure of the overturning that I showed before. You have a positive overturning in the Atlantic, a negative overturning in the Indo-Pacific. But now the contours here are showing a diagnostic of the heat and buoyancy transport. So here these look a little bit different from the overturning because they don't have to go to the zero at the surface. We can have heat being lost across the surface, gained across the surface. And what you see, it's the sign and the structure of this overturning that brings heat into the Atlantic where it's lost at the high latitudes and exports this heat from the Indo-Pacific. So again, this coupling between the basins becomes very important. Okay, so now we want to move back to, again, this schematic picture with this zonally average picture of the overturning circulation. And now I want to focus on this upper cell, or what we call the Atlantic meridional overturning circulation. Again, in the schematic picture, you have this view of deep water being sourced from the North Atlantic, upwelling in the Southern Ocean, where it can be modified at the surface, and then returned back to the Atlantic Basin. Now, when we started working on this problem and thinking about what would be the perturbation to the AMOC during climate change, we came up with what we call this upper cell conundrum, because there are at least two things that we expect to see in a warming climate. The first thing we know from a number of studies is that we expect to have warming and freshening in the North Atlantic, which would predict that we give rise to a weakening of the AMOC because we're removing that process of heat loss from the North Atlantic. At the same time, we know a warming climate is also associated with a strengthening of westerly winds in the southern hemisphere, which is a main driver of this upwelling along these density surfaces. And so that would predict actually an AMOC strengthening. And we weren't quite sure which of these two processes would win out. And in order to look at this, we decided to start with a very simple numerical experiment to gain some insight into what is happening here. So here I'm showing, it's a numerical setup. What you're looking at is a plan view of a very simplified picture of the global ocean. And importantly, it has two different basins. On the left-hand side, you have the Atlantic Basin. On the right-hand side, you have the Indo-Pacific Basin. And the main difference between the two is that in the Atlantic Basin, we have a region in the north where you make dense water. Finally, in the southern part of the domain here, we have some representation of the Southern Ocean that allows exchange between the two basins, and again, has some representation of upwelling in the Southern Ocean. So what this model is actually evolving is just an interface between what we'll call the upper part of the water column, an upper layer, and a lower layer. And importantly, we can also measure the volume transport in and out of the basins. And on the right-hand side here, you can just see a distribution of the surface wind stress that's applied to the Southern Ocean that mimics that upwelling in the Southern Ocean. So what we're going to do for this experiment, the first results I'm going to show you, is do a perturbation that reduces the amount of volume transport between the upper layer and the lower layer in the high latitude North Atlantic. And so this is a representation of a suppression of deep water formation, which you might anticipate would give you a reduction in the strength of the AMOC. So what I'm plotting here is the first response to that perturbation. Again, what I'm actually measuring here is the volume transport across the southern boundary of these basins. So in this case, it's across this dotted line. You can see after the perturbation, what you find is that there is a reduction in the volume transport leaving the Atlantic Basin, and the negative sign here implies a weakening of the AMOC. Interestingly, following this perturbation, the change in Southern Ocean volume transport is relatively weak. So there's not a strong response in the Southern Ocean. But if we look in the Pacific Basin, we get an overturning that has first a perturbation that has the opposite sign of the Atlantic, and it is almost the same magnitude as we have in the Atlantic. So in gray here, I'm just plotting the opposite of this blue curve here. And so what we found is that when you perturb the AMOC, when you have a weakening of the AMOC, on short multi-decadal to centennial timescales, we have a compensated response by the Indo-Pacific, which is an overturning change of roughly the same magnitude, but the opposite sign. As we run these simulations longer, what we find is that eventually the Southern Ocean does begin to respond to the change in the interface depth in the northern basins. And over a longer period of time, that perturbation to the Pacific Basin weakens, and over millennial timescales, the compensation is largely between the Atlantic Basin and the Southern Ocean. So what's actually happening here, this is a little bit of a technical slide for the oceanographers, but what you're looking at now are different lines that are showing the anomaly or the displacement of that initial interface between the upper layer and the lower layer. And so the first key thing to look at here, time moves down as you go from purple to blue to green to red. So following a perturbation in the AMOC, what you see is generally a gradual deepening in the interface depth in both basins, both in the Atlantic Basin and the Indo-Pacific Basin. You also see a lot of structure in this displacement of the interface in this case. This small-scale structure is largely due to the fact that the transport between the basins and the Southern Ocean happens in boundary currents. But I'd like to draw your attention to the overall slope across the basin, which is shown by these black dashed lines. And you can see that in the Atlantic and the Indo-Pacific Basin, the perturbation in that slope has opposite signs. Using a thermal wind relationship, this is implying that there's a zonal density gradient that's part of this perturbation, which implies an overturning perturbation of opposite signs in each basin. We're going to kind of get back into that later in the talk. So this is a rather idealized model that I showed you. I just want to show one slide here that shows that this response also happens in much more realistic general circulation models. So I showed you this picture before, which is the overturning circulation diagnosed in both the Atlantic and the Indo-Pacific basins from CESM. And again, you have this opposite overturning sign. And now what we're going to do is look at the perturbation following the RCP 8.5 emission scenario over the last century. And so as I move to this next slide here, what you're looking at in the lower panels now is actually the perturbation in the stream function. So it still has units of volume transport, but we're showing that in both the Atlantic, which is the middle panel, and the Indo-Pacific basins, looking at the difference between the 2090s and the 2000s. And so what you see in the Atlantic Basin is the sort of response that you expect, that there's a weakening of the AMOC, which is given by this negative overturning response. And yet what we see in the Indo-Pacific, again, is this overturning anomaly that has the opposite sign and to a large extent actually compensates for changes in the Atlantic Basin. Now, it's important to note that this change in the overturning in the Indo-Pacific is largely due to a displacement of the density surfaces. It's a change in stratification that's being propagated between the two basins. We've had a number of discussions with colleagues who talk about, in different climates, might you have a source of deep water formation in the Pacific that gives rise to these overturnings? At least in these simulations, this is not due to identifying a new site of deep water formation, what some people call the PMOC. This is really just a response to the change in the stratification. Okay, so I've talked a little bit about changes in the overturning circulation in terms of a volume transport between the different basins. But if we think about what the ultimate impact these changes have on Earth's climate, you really need to think about what the implications are for changes in heat and other tracer transport. So here, what you really care about is not just the anomaly in the overturning circulation itself, but how it correlates with tracer structure, and in particular the vertical tracer structure at the southern boundary of these basins. So here I'm showing a schematic which shows on the left-hand side a picture of the Southern Ocean and the temperature distribution in the Southern Ocean. And then on the right-hand side, the upper panel is the Atlantic Basin, the lower panel is the Indo-Pacific Basin, and the dotted lines are showing the perturbation stream function that arises from an increase in, that arises from a warming of the atmosphere. So in the Atlantic, we see a counterclockwise anomaly, and in the Indo-Pacific, we have a clockwise anomaly. If I look at the correlation between that anomaly and the temperature distribution, it implies that there's warmer water leaving the Atlantic than coming in, which implies a southward heat transport out of the Atlantic Basin. Whereas in the Indo-Pacific, I have waters moving in shallower depths where it's warm and water moving out where it's colder, which implies a heat transport into the Indo-Pacific and potentially a subsurface warming. And indeed, when we actually go in and diagnose the heat changes in the global ocean following these perturbations, so in this particular case, I'm showing the results from a 4 times CO2 perturbation from CCSM4. On the upper panel here, you see depth in the Indo-Pacific, time on the x-axis, and you can see that accumulation of heat in the Indo-Pacific following this anomaly. This warming is something that you might expect simply because the atmosphere is getting warm. You might have surface heat uptake that is slowly being mixed into the basin interior. But when we actually did the calculation of what are the processes that are leading to heating in the Indo-Pacific, what we found is that the dominant term giving rise to an increase in heat content in the Indo-Pacific was not surface heat uptake. Rather, it was this advection of heat by the perturbation in the overturning circulation. And that's what's shown here on the lower right. You have time on the x-axis. The y-axis is showing the increase in heat content in the Indo-Pacific Basin. And you can see almost 75% of the increased heat content comes from this perturbation in the overturning. So we think of these as adiabatic processes. They are not heat coming into the surface and mixing down into the interior, but rather they're related to stratification changes. And they seem to be dominating rearrangements of tracers on centennial timescales. Here, a sort of interbasin exchange of heat from the Atlantic into the Indo-Pacific. And I just want to show one other example here from a more recent paper that was led by Shantong Sun, which was to think about the impact of these overturning perturbations on biogeochemical cycling. So here we're doing something quite similar. We're imagining moving into a warming climate which would lead to a weakening of the overturning circulation in the Atlantic Basin. Again, that's shown schematically here by this dotted line, and a strengthening of the overturning circulation in the Indo-Pacific or the Pacific Basin. Here now, rather than heat, what we're looking at in color is the distribution of dissolved inorganic silicate concentrations, which interestingly have very different vertical structures in the South Atlantic and the Southern Pacific. You can see that silicate is more or less vertically uniform in the Atlantic, whereas it is a large vertical gradient in the Pacific, which is largely due to the fact that the Pacific is not ventilated in the same way that the Atlantic is. There's no deep water formation in the Pacific. And if we look at the response to that perturbation, so we're running some more idealized experiments, where I'm showing here in a warming climate, you have a weakening of the overturning circulation in the Atlantic basin. You have a strengthening of the overturning circulation in the Indo-Pacific. These are perturbations that are very similar to the ones I showed before. But now we're going to look at the impact of the transport of that silicate nutrient into the Southern Ocean. So in the lower panel here, what we're showing is as a function of time on the x-axis, the transport of silicate across the southern boundary of both the Atlantic basin, which is shown as this blue curve here, and also in the Indo-Pacific basin, which is first shown as that red curve. And so the first message here is that silicate transport is dominated by the Indo-Pacific. The Atlantic makes a relatively weak contribution. And then you can see here that you have two curves. There's a blue and a green curve, and then a red and an orange curve. Well, those are simply showing the green curve is showing that contribution of the transport that's just due to the overturning perturbation, because it could be other processes due to eddy transports, etc. And you can see for both cases, and in particular for the Indo-Pacific, the perturbation in the overturning stream function, the overturning transport, makes the dominant contribution to now the exchange of nutrients between the northern basins and the Southern Ocean. And on the right-hand side now, we're just summing that contribution from the Atlantic and the Pacific in brown and purple. Again, this is dominated by the overturning change. And then this pink curve is showing that there is a slow response to changes in the overturning circulation in the Southern Ocean itself, so that over long timescales, so over about a period of 1,000 years, there's essentially a balance there. But on multi-centennial timescales, there is an accumulation of nutrients into the Southern Ocean. Now, this is actually the response that has been talked about previously. There's a well-cited paper led by Keith Moore in 2018, which talked about this nutrient trapping in the Southern Ocean that can happen in a warming climate. But most of those explanations really hinged on perturbations to the surface wind stress in the Southern Ocean, as opposed to this response to the overturning circulation. So I'm just going to show you here results from one other experiment where we looked at changes in the silicate concentration, both at the surface ocean, which is what these upper panels are showing, and then as a function of depth and latitude in both the Atlantic basin in these middle panels and the Pacific in these lower panels. And we ran experiments where we did both a wind perturbation, so going back to my upper cell conundrum before, a strengthening of the winds in the Southern Ocean. And also on the right-hand side, a buoyancy perturbation that mimics a shutdown or a weakening at least of the overturning in the Atlantic. And I think what you can see pretty clearly from these lower panels is that the largest changes in the silicate concentration do not come from the wind perturbations, but rather come from the buoyancy perturbations. We see here both the accumulation of nutrients at depth in the Southern Ocean, again, which we largely attribute to a southward transport across 30 degrees south from the Pacific Basin, and then it gets homogenized to a certain extent in the Southern Ocean between the Atlantic and the Pacific as the Antarctic Circumpolar Current. But you also see these changes in the northern basins as well, and these look much more, I would say, latitudinally uniform. And what you're seeing here is largely a response to a deepening of the stratification following a weakening of the AMOC. So again, getting back to this change in the ocean's density structure at stratification, having a big impact on these tracer changes. So I'm gonna stop and shift to a slightly different part of the talk, but I think the key takeaway message here is that even if you perturb the AMOC, or have a perturbation to the AMOC locally because you've reduced North Atlantic deep water formation, we have this very important global response. And in particular, that happens over relatively fast timescales, decadal to multi-centennial timescales, because we can propagate these changes in the stratification via coastal waves and coastal boundary currents. So I've talked so far mostly about the global overturning circulation. I want to shift my focus now a little bit more to the Atlantic Basin. Uh, and this has been an important topic because we are, the community as a whole understands that in a warming scenario, we expect the AMOC to weaken. And there's a big question about whether that weakening will be, relative a small perturbation to present strengths, or whether this will be a much more dramatic collapse. And so we're going to probe this over a range of different timescales using a really unique set of climate experiments called the long run MIP experiments. And what I'm showing here just for sort of an introduction is showing the range of AMOC evolution, in this particular case to a 4 times atmospheric CO2 perturbation. Again, over a range of different timescales. So you can see it in the x-axis here. You have a logarithmic timescale, so we're looking at perturbations, everything from decadal to centennial, ultimately to multi-millennial timescales. And on the y-axis is the strength of the AMOC normalized to each of these 7 models' initial strength. So they all start off at 1. And what you see here is sort of interesting. They all represent a weakening of the AMOC in response to this 4 times CO2 perturbation. The magnitude of that weakening varies pretty dramatically between these different simulations. They all show to some degree, except maybe this lowermost sort of mint green curve here, they all show some degree of recovery over long time scales, but this time scale over which that recovery occurs, again, is very different between these models. So we have really large spread across couple GCMs in how the AMOC will respond to different climate perturbations. And we're going to try and probe what sets those different responses. So as I said, we're working with this really interesting intermodal comparison project, this long-run MIP, which was organized by Maria Rugenstein at Colorado State University. And she went around and looked for all of those coupled GCMs that had been run out for at least 1,000 years. And most of these have been run out to 2,000 or 3,000 years. And they needed to be coupled, so they include interactions between the atmosphere and the ocean, as we'll see processes that are happening related to sea ice in the high latitude Atlantic will be important as well. And I'm just showing here 2 plots, 2 time series showing a typical, what we're going to call a strong recovery experiment in CESM1, and what we call a weak recovery experiment in this lower model here. And so we can plot 2 things. On the y-axis here is depth, time is on the x-axis. The colors here are showing the strength of that overturning circulation, and this black curve is a proxy for the depth of the AMOC. And so you can see here in all of these experiments, you have a weakening of the AMOC and importantly, a shoaling of the AMOC on decadal to centennial timescales. And then again, where there's real variability in these models is during this recovery stage. In some models, the AMOC strengthens, and in fact, it's even stronger than its initial state. And in some cases, the recovery is rather weak, at least over the timescale of which the models have been run. So our focus on this particular study goes back to thinking about the stratification. And so in particular, thinking about how the ocean stratification in the Atlantic Basin is related to the strength of the AMOC. So what I'm showing here on the upper panel is a zonally average picture of the density in the Atlantic Basin from CES1. So again, depth is on the y-axis, latitude now on the x-axis. You can see that these density surfaces are mostly flat throughout the Atlantic Basin, but as you get into the high latitude North Atlantic, places where you have cooling, where you're making deep water, you can see that there's a tilt in those density surfaces that gives rise to a north-south density difference. Now we know in the ocean at large scales, the ocean is governed by the thermal wind equation, where we can relate a north-south density difference to a vertically sheared velocity. Now, what I've written down here looks almost like the thermal wind relationship, but there's something wrong here because we know if we're thinking about a north-south density difference, thermal wind would tell us this is related not to a north-south velocity or meridional velocity, but rather to the zonal velocity. We would expect an upper ocean flow that's eastward and a deep ocean flow that is to the west. Now, one thing that is sort of a remarkable feature of the AMOC is that this thermal wind relationship does seem to work very well if you use the meridional and north-south velocities here that we typically associate with the overturning stream function. This is very much still an area of active research, but the general sense here is because the Atlantic Basin is bounded to the east and west, that this zonal thermal wind transport that I'm showing here with these orange circles does need to be largely in balance with the north-south flow, because as that eastward, upper ocean eastward transport moves towards the eastern boundary, it will turn to the north and sort of form that upper limb of the overturning. Similarly, as waters flow out of the Arctic, they will move both west and southward along these deep western boundary currents. So we're going to use this relationship to sort of understand changes in the overturning circulation, and we're going to look at how density differences between the North Atlantic, so in this region between 30 degrees south and between 30 degrees north and 60 degrees north, changes with the lower latitude density. And so on the right-hand side here, I'm just plotting what that difference in density between the north and what I'm going to call the low latitude basins looks like as a function of depth. And so I can take this density difference, I can take this equation here, I can integrate it twice with respect to depth to move from a vertically shear velocity to a transport, which is the overturning transport. I have boundary conditions at the top and the bottom, which is the stream function has to go to 0 at the top and the bottom. And it allows me actually to reconstruct the overturning circulation using this thermal wind relationship. That's what's in the purple curve. And you can see there, at least comparing that in CESM1, it tends to do a pretty good job. And then we've sort of probed this relationship over longer timescales. Here we're showing the overturning transport as diagnosed exactly from CESM1 over a period of a few thousand years, and then also as would be diagnosed from this thermal wind relationship. And you can see that it's not always perfect, and especially over shorter timescales, there's some difference between those two, but at least over centennial timescales, this relationship holds really well. And in fact, if you actually look at the trend over these different gray bars here, the correlation coefficient is very good between these two different estimates of the overturning. Okay, so let me show you a few results here from this analysis. So let me walk you through what you're looking at. We had 7 different models that we looked at, and what we did is we broke up this evolution of the overturning into a few different phases. And the first is this initial weakening phase, which occurs during roughly the years 50 to 80 after the perturbation. And the first thing to look at here is the purple bars, which are showing the change in the strength of the AMOC during this initial weakening phase as compared to the initial strength of the overturning, so say between years 1 and 10. In all of these experiments, you get a weakening of the AMOC. That's to be expected. And if you look at these black curves, you can see that the strength of the weakening is largely correlated with a reduction in that north-south density difference. And that is largely due to warming happening in the northern Atlantic basin. And that's what these red and blue curves are showing here. We can take now this difference in the density as given by these black bars, and we can break it up into a thermal component. So how much of that change in density is due to differential heating between the north and the low latitudes, and how much is due to a haline component or a freshwater flux. And you can see, at least during the initial weakening phase, that the change in density is dominated by heating, and that mostly happens in the northern part of the Atlantic. And again, that seems to be consistent throughout all the models, even though the response is a little bit different. If we then look at a period that goes from roughly years 470 to 500, what we call a partial recovery phase, we see a very different picture. So first of all, we see a slightly different range of AMOC changes. Again, these are compared to the initial strength of the AMOC. So we have a range of models where the AMOC still remains weak. We have others where the AMOC has already started to recover from its initial state. You can see that those changes correlate very strongly with the density difference, which is in black. It's what we expect based on our thermal wind relationship. But now you see a really different contribution from the warming, the thermal component, and the haline component. And they have very different responses. So now here we see that all of these red bars are positive, which implies that differential heating should be starting to re-strengthen the AMOC. We should be warming the low latitudes, re-establishing that density gradient and turning the AMOC back on, but that's being opposed in most of these models by a freshwater flux. And in fact, if we actually look at a longer time recovery, okay, what we see now here over the periods 470 to almost 1,000 years, almost all of these models now experiencing some positive trend in the AMOC. They're all experiencing some recovery. That's what's shown in these purple bars. But some are much, much stronger than others. And what we found is that that recovery trend is very strongly correlated with how much Arctic sea ice is remaining in the North Atlantic. In those models where most of the sea ice melts, it is a much, much slower recovery for the AMOC than in those models that retain some of its sea ice. And so our explanation for that sort of looks like this. I'm showing at the top sort of example time series of an AMOC that has a strong recovery, and on the right one that has a weak recovery. And the story for temperature, I think, is one that's been talked about in the literature quite a bit, which is that we have this, and so time here is on the x-axis, latitude is on the y-axis. So you're seeing the perturbation in temperature in the Atlantic basin. You have this early warming in the high northern latitudes, which reduces that density gradient, weakens the AMOC. But in both models, in both of these strong and weak recovery models, over long periods of time, you have a lot of low latitude warming. Part of that happens in the Atlantic. Some of this might happen in the Indo-Pacific and be transferred into the Atlantic. But that reestablishes this north-south density gradient that would act to intensify or allow the AMOC to recover. But in some of these models, it's opposed by the freshwater flux. So the big difference here in whether the AMOC has a strong recovery or a weak recovery has to do with the high latitude freshwater flux. In those models where sea ice does not go away completely, you can see that the freshwater perturbation in the North Atlantic is relatively weak, and we have a strong recovery. Whereas in those models that have a weak response, you have a much stronger perturbation in the freshwater flux in the high latitudes, and it takes a much longer time to erode that freshwater anomaly, largely through advection of salty waters from the lower latitudes in the Atlantic. So one of the takeaway messages from the study was to think about, although these models might be doing something very similar for the ocean, its coupling to other components of the climate system, in this case, sea ice, has a really big impact on both the degree of AMOC weakening and also the timescale over which it recovers. And so for just the last part of the talk, I'm just going to spend the last 5 minutes here talking about one piece of new work, which is now going to zoom in on this weakening phase. So we're going to move away from the sort of long-term recovery of the AMOC, but thinking about what is the AMOC's response over the next roughly 100 years. And so what I'm showing here is kind of an interesting result. These are the response of a range of different CMIP6 models. In fact, it's all of the CMIP models to a number of different shared socioeconomic pathways. So on the left-hand side is sort of a more gradual sort of climate scenario in which the warming is not so strong, a sort of moderate case in the middle, and on the right-hand side, you have a much stronger perturbation. What you see in all three panels is that the distribution of the curves doesn't look very different for the different forcing. So at least over the next 100 years, the evolution of the AMOC, at least as predicted by these CMIP6 models, is actually not very strongly dependent on the forcing itself. And yet if we actually look at the magnitude of the change in the AMOC, the response to these different forcing scenarios, you can see that there is still a strong range of responses across the different CMIP6 models. And what Dave Bonin, who has led this work, has done here is he's sort of separated out those responses into those models that have a strong response, shown here in red, a moderate response in black, and a weak response in blue. And you can see that these are all pretty similar in all of these different forcing scenarios. So the question is, what is sort of differentiating these models? What's giving them these different model responses? So to do that, we went back to our thermo-wind relationship that I showed you before. Remember that vertically sheared velocity was dependent on a density difference. And when I showed you some of the results from that scenario, the density difference did seem to be pretty strongly correlated with changes in the overturning, but it wasn't perfect. And when we revisited this relationship, we realized, of course, that if you form the stream function from that thermal wind relationship, you also get a contribution here from sort of the thickness of that upper layer. You can think about it as the stratification. So this here is a sort of common scaling that's used for the strength of the overturning that, again, depends on this north-south density difference, but also has some relationship to the vertical structure of the stratification in the Atlantic Basin. One thing we can look at now is we can actually look at what is the perturbation of, how does the perturbation of the stream function depend on changes in this density difference versus changes in the ocean's vertical stratification. And so what I'm showing in this orange box here is that we can do essentially a Taylor expansion here for the stream function by decomposing the change in the overturning into changes in the density difference, which is this term A, and a term that's related to the changes in the stratification, or what we'll sort of call the depth of the AMOC. And then there's a residual term here, E. On the left-hand side, I'm just showing that actually if you just diagnose the change in the overturning and attribute it to these different terms, you actually do a pretty good job of recovering the changes in the overturning. So this scaling here, you might think of it, seems to do fairly well. But sort of the key takeaway, if I go to the next slide here, these are all the different CMIP6 models that we looked at, and I realize there are a lot of bars here, but what we're looking at on the y-axis is the change in the AMOC, that correspond to these dots in the upper left-hand panel, divided up into the models that have a weak response in blue, moderate response in black, and finally a strong response in red. And then finally, for each of these models, we've attributed the change in the overturning to both the change in the density difference, which is this term A, or this open bar here, or a change in the stratification, which are these hatched bars. And the kind of key takeaway here is that it's actually not the north-south density difference that has a strong control in the overturning perturbations, at least on this 100-year timescale, but rather the vertical change in the stratification of this perturbation to H. And that vertical length scale here, H, is very strongly related to the stratification in the North Atlantic. So what I'm just showing here again is those models that have a weak response to the perturbation, a moderate response, and a strong response. And you can see in all of those weak responses, you have a very strong vertical stratification in the North Atlantic that impacts the depth of the overturning circulation. So I'm going to just move on to kind of the last result from this paper, and then I'll wrap up and be happy to take questions. What's nice about using this thermal wind relationship, there have been a lot of studies that have looked at the potential for the AMOC to collapse. And most of those have used very statistical approaches to estimate, are we seeing, say, increased variance in the overturning circulation as a predictor for whether we might expect to see an AMOC collapse? I think what's nice about using this thermal wind relationship is it gives us a physical relationship that helps us to understand what are the terms that are contributing to the changes in the AMOC. And so when you have this physical relationship, you can use something called an emergent constraint approach. And the idea here is that if you can relate changes to current day properties, one can look at observations that sort of give us information about those current day properties and sort of constrain which models might be more realistic. So what I'm showing here now is on the x-axis is the range of present day AMOC values as represented by the CMIP6 models. So those are these black dots, and they are plotted against the change in the AMOC under this perturbation. And here I'm just showing the sort of moderate forcing scenario. It has been pretty well known and recorded in the literature that there is a strong correlation between the present day strength of the AMOC and the actual change in AMOC. So for stronger present day AMOCs, you tend to get a larger response. For weaker present day AMOCs, you tend to get a weaker response. And the simplest thing you could do here is actually just fit, do a linear regression to these different models to give you the potential spread for the changes in AMOC. And so that's what's shown here as sort of this gray curve with these blue bars showing 2 sigma standard deviations. And you would get, in terms of a distribution of potential AMOC changes, this black curve here, which is fairly broad, but predicts a pretty substantial AMOC weakening on the order of, say, 8 to 10 sphertrops. If you instead use the constraint for the thermal wind expression, you get a curve that's slightly different. So it's no longer linear. It has some curve here and does a slightly better job of capturing the sort of large or the strong response experiments in this case. And more importantly now, we can use some observational estimates, and we have actually chosen to use the ECHO model, which is an ocean state estimate that is data constrained. We have also looked a little bit about look at the strength of the overturning at the rapid array. We can actually use those observations to get an estimate of what actually the present day distribution is in the AMOC. And what you see here is that falls somewhere between, say, 12 and 18 sphertrops, a mean of about 15 sphertrops with some distribution. And if we use those observational constraints, we get these orange predictions here for what the range of AMOC perturbations we might expect to see based on our present-day AMOC. Of course, there's still a wide range here, a wide distribution, but what we find is that the predicted weakening, again, based on the present-day AMOC in this thermal wind constraint, is considerably weaker than what would be predicted simply by looking at all of the CMIP models together. And so what we think is, based on this relationship between the importance of stratification in the North Atlantic, we can eliminate some of these models, which we think have a bias, have a much stronger response in terms of its AMOC weakening than we might expect in the real ocean. So, of course, I think this is, one contribution to understanding what the changes look like. This is a paper that's currently in review, as led by, as I said, Dave Bonin, and I'd be happy to answer any questions about that as we just wrap up the talk here. So I'll just leave my conclusions up and sort of talked about 2 different pieces of the work we're doing. First is this sort of interbasin response between the Atlantic and the Pacific. And the second one is sort of understanding what are the physical processes that control both the weakening and potential recovery of the AMOC over a range of different timescales, spanning decadal, again, up to multi-millennial. And maybe just to close, I'll say what we've learned is that the ocean's stratification, it plays a really crucial role in understanding what the global response is to perturbations, whether they're localized perturbation or global perturbations in these experiments. And so I think these are important places to go to look for biases in different climate models. How well are they accurately representing the ocean stratification? And again, we're using the Argo data array, and in particular going forward with Deep Argo, we're going to have a lot of information about where we can improve models in their representation of ocean stratification. Okay, I think this is a good place to stop. Thanks very much for your attention, and I'd be very happy to take questions.
Thanks, Andy. So if anybody has any questions, you can go ahead and raise your hand or put your question in the chat, and I will read it out loud. Or everyone has the ability to unmute themselves, so they can just go ahead and ask it. Go ahead, Reed.
Hi, thank you so much. That was a super interesting talk. I loved like the 3D perspective of like the Atlantic and the Pacific. I'm a graduate student looking at Arctic sea ice and sea surface height observations from altimetry specifically. And I was really interested in the mechanism of how the AMOC recovery is related to the freshwater or the saline component. And I was wondering if you could say a bit more about whether that's directly due to sea ice melting, or because also stratification changes through the thermal component maybe, or and maybe or maybe how for example Greenland melting is represented in these different models.
Yeah, thanks for that question, Ray. I think it's a really nice question. So what I showed here is we did, so for this 2022 paper, the main focus was actually decomposing the stratification changes, really the north-south density differences into both thermal and haline components. And I should note here that we'd be a little bit cautious. We assumed a linear equation of state. We assumed constant thermal and haline expansion coefficients. But I think the dominant contribution here from the freshwater flux does come from the sea ice belt. There is, and because you're at high latitudes and you're mostly in a salinity stratified regime, my impression is that the stratifications are dominated by changes in the sea ice and those freshwater fluxes. There are some interesting questions here about where you do your averaging of your sort of freshwater forcing. And of course, as you know well, a lot of the transport happening in the Arctic is occurring via boundary currents, and the representation of those boundary currents in some of these models may or may not be very accurate. What was interesting is that our results were relatively insensitive to choosing different averaging areas. And I don't think we understand that terribly well in a physical sense, but it is something that we were looking at the sensitivity of our results to that, and they seemed rather robust. And I think that may just be a feature of the timescales that we're looking at, that over sort of multi-decadal to centennial timescales, there's enough mixing going on that the models are not super sensitive to where you do your averaging.
Thank you. And then I was wondering about the Greenland melting. Is that realistically in these models on those timescales? I assume so. Are there large differences there in terms of like the freshwater pulse or?
Yeah, that's a good question. I must admit that off the top of my head right now, I'm not sure what all of these models are doing for their freshwater input from the Greenland ice sheet. My sense is that that is small compared to the changes you're getting from the Arctic sea ice, but that is something I would need to go back and check.
Okay,
Well,
thanks
that's a good
anyway.
question. Yeah,
Yeah, thanks again.
you're welcome.
Thank you. So Paige Lavin, you can go ahead and ask your question.
Hey, Andy, thanks for the great talk. I was curious. So my kind of takeaway here was that under these different scenarios, we're likely to see some AMOC weakening and then a likely recovery, but not a total AMOC collapse, as some headlines would suggest that we're facing. And so what I was curious about was, whenever I think about AMOC collapse, I think about Carl Wunsch's, the Gulf Stream is safe if the wind blows and the earth is turning paper from like 20 years ago. So would you say that, I know there's a lot going on here, but would you say at broad brush that's true? It seems like we're unlikely to ever really have a full-on AMOC collapse here.
Yeah, so I think there's kind of two pieces, and maybe I'll go to a schematic in a minute. Let me can I add my my flavor to Carl Wunsch's statement, which is, I think what really is a driver here, right, is this north-south density difference that I tried to emphasize in this talk. And if you're thinking about the overturning, it's often useful to think about it in terms of think about it in density space and where water mass transformation is happening. And of course, that is imbalanced to a certain extent with the winds. But I do think that even if you have a perturbation in the AMOC, you very quickly get back into the scenario where the low latitudes are accumulating heat. And for the ocean to come into some steady state, it has to redirect or redistribute that heat into places where you can have heat loss. And so that's what I see as sort of the principal driver of what turns the AMOC back on, right? And so then it's largely the fact that it, in some models it has to fight against this large salinity gradient that has been established, and others it doesn't.
Right.
So it is that accumulation over time of just heat in the low latitudes. Again, we didn't probe this in detail in the long run experiments that I showed, but again, I think this largely comes from most of that heat uptake happens in the Indo-Pacific and is being brought into the Atlantic Ocean.
Okay, so maybe add, as long as the sun shines on a tilted Earth, the AMOC will continue.
Yeah, maybe that's a good way of putting it, Paige. That's a good way of summarizing it. Yeah.
Cool. Thanks, Andy.
Yeah, I'll maybe just leave the schematic up because I think it responds. I didn't have a chance to show it in the main talk, but I think it responds to the past two questions, which is just this idea that, in those models that have a weak North Atlantic stratification, the AMOC's already quite deep. And so if you have a perturbation in the North Atlantic, it's going to have a much stronger change in the AMOC. And we think that some of these models that have a large response are sort of a bias to have a stratification that's too weak in the North Atlantic. And that's why we're kind of suggesting from the emergent constraint approach that we may not see a huge reduction.
Great. Thanks, Andy.
Yeah, thanks, Paige, for the question.
Thanks. Does anybody else have any questions? You can raise your hand, you can type in the chat. Okay, well, unless anybody else has any questions, I think we are good to conclude. So thank you everybody for coming to this great talk, and thank you, Andy, for calling in all the way from Caltech to give us this talk. This was great. Everybody else, our seminar series continues, same time, same place next week. Oh, is that not true? Is it on Tuesday, John? Is John still here? No, it is true. It's on Monday. The one after that is on Tuesday. Okay. Thank you, everybody. Have a great afternoon.
Thanks for coming, everyone.
Bye.
Bye. Thanks, John.